So hello everyone again and welcome to my channel, where today we'll be looking at LA system. And in our previous video where we looked at butadiene which has even number of carbon atoms with p orbitals, and p orbitals which are very important in the formation of a conjugating system for the enhancement of cycloaddition reactions. Now that was quite easy because we're able to form molecular orbitals combinations through our Fourier molecular orbital system in our way to generate this HOMO and LUMO that were critical in cycloaddition reactions. Now the tricky part is when you're given an odd number carbon atom system, how are we going to be able to generate molecular orbitals, and how will this be important in terms of introducing some kind of interesting tweaks in this particular molecule to form our desired compound. Now, what are the tweaks involved? Let's say, for example, we are given propane, and propane, as you know, is a 3 carbon atom where our carbon 1 and 2 has p orbitals, and this p orbitals is quite important in formation of this pi system over here. However, the third carbon doesn't have that at all. What it has is just an sp3 carbon atoms where there is no p orbital here at all. So there is no p orbital here. Thereby, there is no conjugation between our carbon 2 and our carbon 3. Now, how are we going to be able to make this to be activating? How are we going to activate this? A good one way of activating this is by using or reacting this compound with a very strong base. And what that strong base does is that it deprotonates the hydrogen which is around this particular sp3 carbon over here, thereby generating a charge. Now, quite fascinating, because if you're able to do just that, we're going to be able to transform our sp3 carbon into our sp2 carbon. And once you're able to do just that, then we'll be able to generate our p orbital that will be crucial in our way to form this nice conjugation system alongside our planar system as well. So let's look at the reaction process over here. So in here we have hydrogen here, and it's attached to this carbon, and this carbon has a pi system over here with this other carbon number 2 and our carbon number 3. I'm just going to draw this just to show that this is planar, and why this particular region is not planar at all. Now, once you introduce a base with a negative charge on it, what happens then is that this base extracts this hydrogen atom, and what happens then is that this bonding pair becomes a lone pair in this particular carbon. And what happens is that we have a proton removal, and this proton that's removed leads to the formation of this particular product over here with a negative charge on it, and we have our pi bond over here, and we still have our hydrogens over there and over there. Now, what you notice here is that there's a transformation in the geometry of this particular molecule, where on carbon 3 we initially had our sp3 carbon with a tetrahedral shape over here. However, it's been changed into our sp2 carbon with a trigonal planar shape over there. And now what happens then is that we are transforming our propene into an Allyl anion, where we have our negative charge over there with lone pairs Thereby what happens then is that you're including 2 electrons into this particular overall compound that is having a p orbital, and that p orbital in this region over there will generate a nice conjugating system, making it to form 3 sp carbons over there. So when you're going into now our 3 carbon system, then we're going to note the 3 possible molecular orbital combinations that will be crucial in this case. So in here there's quite different here, because in here we have 3 atomic orbitals that are from the 3p or 2p carbon atoms in here, or 2 over there, and this leads to our 3 molecular orbital combinations that are important. However, what we have now is that although we have 3 in the molecular orbital combination state, since we have our deprotonation of a hydrogen, which leads to the donation of 2 electrons to the initial 2 electrons present in the p orbital system, what results then is that we're going to have 4 electrons to be distributed within these 3 molecular orbital combinations that we have. So let's draw our energy scale to look at what are the 3 possible ways of actually generating our molecular orbital combinations. So in our energy scale we have 1, 2, 3, and now you have to note that we are increasing in the number of nodes, where number of nodes in the first energy scale is 0, while the other one is 1, and the next one is equal to 2. And what we have here is we have our first one where all the 3 are in phase with respect to each other, because we don't have any node at all. However, in the first one we're going to have 1 node. Now this is quite tricky because we don't know where to put our node, whether it's at the center where there's an orbital over there, or we're going to have it either on the sides. We can't put it on this side because these sides here it will be non-symmetrical, but we need to generate a symmetry. Now what happens here is that there is a non-bonding case here, where there's an orthogonal case where this orbital here is orthogonal to this particular orbital, and this orbital over here is also orthogonal to this other side over here. This is quite invisible because I don't want to make you guys to see it clearly, but in here what that is that we form a node in this region over there, and what happens then is that we're going to have our in phase and we're going to have our out of phase over there. So therefore in this particular region we're going to have our number 1 node over there. Then our other carbon or combination over there, we're going to have 2 nodes, quite easy to generate. Have this over there, that and that, all of them out of phase with respect to each other. So you see here that the first one and the last one are easier to actually combine, because our first one is in phase with respect to each other, but the last one are all out of phase with respect to each other. But this one is quite tricky, and you need to be able to know how to introduce that symmetry in respect to the node positioning, and also noticing the presence of non-bonding that generates the formation of our node in that particular center of that region over there. So now you're able to see just that. Now let's look at how we'll be able to form a much more efficient propene in terms of including this particular formation of molecular orbitals. Now there are 3 ways of doing just that. One way is either generating an anion to activate our propane. Second way is by generating a radical to activate our propane, and lastly is to generate our cation to activate our propane. Now all their energy levels are pretty much similar or the same with respect to each other, where all these three possible ways of activating our propane will all have three molecular orbital combinations, and their energy levels are pretty much the same, but the only difference is just the number of electrons that these particular guys they have. Now in an anion we are introducing a negative charge and 2 extra electrons, which is what we have over there. So in here we're going to have 4 electrons. Let's put 4 electrons over here, pair the bottom one, then pair the first one. Now once we pair the second one, what we have now is that we have our HOMO present over here, and this part here is automatically our LUMO in this part over here. Now the radical over here now is that radical will have 3 electrons in this case, where we remove a hydrogen with 1 electron over here, and the 1 other electron is then included into this particular region over there. And let me just draw it here properly. Yeah, we have this over there, and we just have our hydrogen and our hydrogen over there. Yeah, so what happens here is that since we have 2 electrons, we pair the first one, and then the second one we add 1 electron, which is unpaired. What we get here is our SOMO. So the SOMO means singly occupied molecular orbital, and this SOMO is what we have over there because it's just singly occupied in this higher energy level over here. But here we have our LUMO over there because it's the lowest unoccupied molecular orbital over there. And lastly we have our cation, which is positively charged, and if it's positive charged, it means that you're removing just the whole hydrogen atom with the 2 electrons, thereby forming a positive charge in the 3rd carbon. And we still have our 2 hydrogen atoms in carbon 1 and 1 hydrogen atom in carbon 2. Now what we do by filling our electrons here is filling our orbital is by adding our 2 electrons in this particular region there, where this is our HOMO and that is our LUMO. So these different ways of filling our electrons with respect to activating our propane is quite crucial in order for we to activate propane and making it to be much more relevant in various cycloaddition reactions in organic chemistry. So that's about it for Allyl systems and how this is important in cycloadditions. I hope you're able to understand it. Please don't forget to hit the like button, share and subscribe, and let me hear your thoughts about this. Have a good day. Peace, love you all, and see ya on my next video. Stay smart.